Okay, so we have now officially moved to our chapter 7. This is the point in the curriculum where things will start to get a little bit more challenging, but I'll try to make it as straightforward for you guys as possible. Today, we're going to focus on our section 7.1, which is angles and really building up this vocabulary before we jump into utilizing it from a right triangle perspective and then exposing you guys to our famous unit circle and then our trigonometric functions. Okay. Our objectives for today are the following: being able to draw angles in standard position, being able to convert between degrees and radians, a very, very important goal that we're going to accomplish. And then finding coterminal angles and the lengths of circular arcs. This is a famous formula that we'll talk about, and we'll tackle some concrete examples towards the end of this section today. So let's first talk about some vocab. We have array, and array is essentially a line, but it extends indefinitely in only one direction. So it contains an endpoint. And so you can have array shooting off to the right indefinitely, or you can also have array that shoots off to the left indefinitely. Okay. The starting point of array, aka the end point, is known as the vertex. So this little guy is your vertex. And then we have when two rays are drawn with a common vertex, they form an angle. So what does that look like? We have a ray here, and then we have a ray here. Oh, what do we have? An angle. We'll call this angle theta. We call one ray of an angle the initial side. We have our initial side, and then the other angle is known as our terminal side, which we're going to be utilizing a lot in this section and later sections. The angle formed is identified by showing the direction and the amount of rotation from the initial side to the terminal side. So it can go all the way around. Think coordinate plane and think circle, aka unit circle. Foreshadowing. If the rotation is in the counterclockwise direction, the angle is positive. If it is clockwise, then it's negative. So it's sort of like opposite. And I'll highlight those. So counterclockwise, positive, clockwise, and our angle is negative. And we'll be practicing a lot of this too. So here are some more visuals. Terminal side, initial side, very similar to what I drew on the previous slide. And we can extend this terminal side in the counterclockwise direction in order to have a positive angle, which this is actually representing visually this way because the arrow's this way. Or we can do it in the clockwise rotation. So now it's going this way, and our angle would be negative. You'll see a lot of these Greek letters throughout these next sections, and it's just ways to denote certain angles. So think about them as variables, but we use them to represent angles. And that's sort of universal across the board in all different countries. The most common angle measure when we learn about really the fundamentals of mathematics, we start out with our theta. And then as we build up higher and higher, then we'll incorporate beta or phi or alpha or gamma, so on and so forth. Some more vocab. The measure of an angle is the amount of rotation from the initial side to the terminal side. And we have 1 degree represents 1/360th of a circle, aka a circle is 360 degrees. So just think about fractions here. And then we also have an angle is in standard position, first objective, if its vertex is located at the origin and its initial side extends along our x-axis. So we have some standard position angles here. X-axis stems from origin, terminal side. This angle is in standard position. Once again, x-axis stems from origin, terminal side. This angle is in standard position. This angle happens to be negative, this angle happens to be positive, but they're both in standard position. And so now drawing an angle in standard position, you just have to check off those requirements that we stated a few seconds ago. Okay, the first one being draw the initial side along the positive x-axis. And then you place your terminal angle anywhere based off of what angle you want to draw. If you're drawing 30 degrees, then it's going to go counterclockwise 1/3 of the way between our x-axis and our y-axis. That fourth quadrant is 90. So 1/3 of the way gives you that 30 degrees. They started off with an easier example of just 90 degrees where you literally have your terminal side on your y-axis. Maybe I'll draw that here. So this is your terminal side, this is your initial, and then we have that 90-degree angle, right? They also represented it over here. When an angle theta is in standard position, either the terminal side will lie in a quadrant, in which case we say that theta lies in that quadrant, or it will lie on the x or the y axis, in which case we say that theta is known as a quadrantal angle. So our quadrantal angles angles that have terminal side lying on an axis. Okay, so famous ones, 0, 90, 180, 270, 360. So now we arrive at our first example for today, where we are asked to sketch these two different angles. We want to sketch out 30 degrees in standard position, and we want to sketch out 135 degrees. So let's create our coordinate plane. And so we're always stemming from this origin. 30 degrees, kind of did this a few examples back, but it's 1/3 of the way through our first quadrant, right? 1/3, 2/3, 3/3. 1/3 of 90 is 30 degrees. This is our terminal side. This is our initial side, and we're done. Now, -135 we want to go clockwise. We know that this whole quadrant gives you negative 90, and then negative 90 plus what number gives you negative 135, an additional 45, which is half of 90, so half of a quadrant. So we know our terminal side now is gonna be at this halfway marker. And now we're looking at this angle being 135. Again, terminal side, and then our initial side. When we're done. We're now on to our second objective, which is dealing with converting between degrees and radians. And so in a lot of the higher level mathematics, we like to use radian measures, so it's important to know the conversion. Degrees is more elementary, and so let's formally define a radian measure, and then I can get into some ways to help remember the conversion rate between the two. So if a circle of radius 1 is drawn with the vertex of an angle at its center, then the measure of this angle in radians is the length of the arc that subtends the angle. So our radian measure of theta is this red length. And if you think about it, right, we know that the degrees of any circle is 360. So 360 degrees in a circle. And this represents 2 pi, aka our circumference is 2 pi here. And why is that the case? Well, what do we know about the circumference of any circle? Cherry pie is delicious. And we're dealing with a unit circle that has a radius of 1. So if our radius is 1, then our diameter is double that, which is 2. So that's how we get the pi times 2, which is 2 pi. Which then tells us that our conversion is, okay, well, if 360 is equal to 2 pi, then pi is the same as 180 degrees. Then you can utilize your knowledge of fractions to really get into the famous angles. So half of pi, also known as pi over 2, is half of 180 degrees, which is 90. Okay, well, what about a quarter of pi? Well, what's half of 190? Not 190. What's half of 90? 45. So pi over 4 radians, right? These are all radians here. Is 45 degrees. Let's go back to 90. Or let's go back to pi, right, is 180. And then what if we divide that by 6? What's pi over 6? Well, what's 180 divided by 6? That's just 30. All right, well, what's 180 divided by 3 then? Pi divided by 3, that gives you 60. These are all of the famous ones that you should know. So really getting comfortable with your fractions will make these sections a bit easier. I will also teach you the general formula for how to convert from radian to degrees or degrees to radians. I'm guessing they might have a slide on it on the next page. No, this next page was exactly what I was telling you about. with the whole circumference of a circle. And then from there, being able to use your fraction knowledge. Rotation just means, okay, how far along the circle are you going to get? But I believe we have, in case they don't, I'm going to create another slide just doing the conversion. If they have it, then great. So if we want to convert from degrees to radians, what do we have? And then if we want to convert from radians to degrees, what do we have? Okay. So think degrees. That's what we're starting out as. And then we want to go to radians. So in our radians, we have some form of pi, which means our degrees, we got to multiply this by pi. And then we're dividing by, well, with radians, it's fractional. So the common number that we'll be using is 180. We're dividing this degrees by 180 to figure out that fractional relationship. And so that will give us our answer in radians. Whereas our radians, it's just the opposite, right? Radians has pi. So now when we go into degrees, we want to get rid of that pi. So we're going to divide our radians by pi. And then we want it in degrees, so we want to multiply it by 180. So these are just the general formulas. In addition to knowing the measurements in degrees and radians, knowing the rotations, quarter revolution, a half, a full, these are the common multiples that we will always be referring back to, especially when we get into our reference angles. And so this is where our unit circle really starts to form. We see these fractions. The quadrants are cut into both thirds as well as cut in half. And it's just reflected and repeated in each quadrant. So that's where we get the 30, 60, 90, 120, 150, or the 45, 90, 135, 180, so on and so forth. Now, let's tackle example 2 together. We want to find the radian measure of 1/3 of a full rotation. Well, 1/3 of a full rotation, remember, full rotation is 360. 1/3 of 360 is just 360 divided by 3, which gives you 120 degrees. But we want to put this in terms of radians. So, degrees to radians. We want it to be a fraction now, so we divide it by 180. And we want it to have radians, so we multiply it by pi. There's a 0 in the numerator and denominator, so we can cancel that out. And then we're left with 12 pi, because pi is just pi over 1, all over 18. But we can simplify this a little bit more because you can pull out what number goes into both 12 and 18. You can pull out a greatest common factor. Right? Doesn't 6 go into both? 6 goes into 12 2 times. 6 goes into 18 3 times. So we get 2 pi over 3 radians, and this is your answer. I'll zoom in on it. And so we do have the formal slide of converting degrees and radians um, between one another. So degrees to radians or radians to degrees, which is what I created the slide on a few slides back. So we don't have to review it again, but feel free to screenshot this if this is a bit more clear. And now let's jump into example 3, and we're just going to practice converting from radians to degrees. I think what I'll do is I'll do it just one by one. Pi over 6 radians, right? Degrees, we want to get rid of the pi, so divide by pi, multiply by 180. 180 divided by 6, because the pi's cancel out, just gives us 30 degrees. And we're done. 3 pi over 2. Once again, get rid of the pi, so divide by pi, multiply by 180. The pi's cancel out. We can also state that 2 goes into 180 90 times, 2 goes into 2 1, so that we just have to multiply 3 and 90 to get 270 degrees. Makes the math a little easier. Part C, negative 7 pi over 4. Multiply this by our 180 over pi. Pi's cancel out. 4 goes into 180 45 times. And then negative 7 times 45, that's the same as negative 280 minus 35, which is negative 315. Now to our D. Three goes into 180 60 times. 7 times 60 is 420. And then last but not least, we have E. 3 radians, and we want to convert it into degrees. So in this case, we're going to end up having a pi in our degrees. Unusual, but it sometimes happens. 3 times 180 is the same as 300 plus 240, which is 540 over pi degrees. And that's it. Do you have to put the parentheses? No. But I just have it there. Now let's look at example 4, which we're going to be converting from degrees now into radians. So instead of dividing by pi and multiplying by 180, we're going to be dividing by 180 and then multiplying by pi. 60 as a fraction is 60 over 1, and then dividing by 180 multiplied by pi. Zeros cancel out. 6 over 18 is the same as 1 over 3. So we get pi over 3. Let's go to B. 150 times pi over 180. Again, zeros cancel out. We can divide the top and bottom by 3. And so 3 goes into 15 5 times, so we have 5 pi in the numerator. 3 goes into 18 6 times, 6 in the denominator. 5 pi over 6 is the same as 150 degrees. Let's move on to C. Negative 45 degrees times our pi over 180. Well, we know that 45 goes into 180 4 times. So we get negative pi over 4. Part D. We have 90 degrees. Good old pi over 2. But I'll show it to you. All right, 90 goes into 180 twice. So we get that pi over 2. And then finally, 107 divide by 180 times pi, which I believe 107 divided by 180 is in simplest form. Yeah. So our answer is just 107 pi divided by 180. And again, all of these are in radians for your units. And we're done. So we're now on to our third objective, finding coterminal angles. And so I guess I'll read this part, but then we'll go into what the definition of a coterminal angle is. We have converting between degrees and radians can make working with angles easier in some applications. For others, we might need another conversion, aka this is where coterminal angles come into place. Negative angles and angles greater than a full revolution are more awkward to work with than those in the range from 0 to 360, or in terms of radians, 0 to 2 pi. And so it would be convenient if we can replace those out of range angles with the corresponding angle within the range of a single revolution. And that's how we are brought to coterminal angles. They're just angles, more specifically two angles in standard position that have the same terminal side. How do we get these? We either add or subtract 360 from a degree standpoint, or we add or subtract 2 pi. If you end up plugging in these values into a trigonometric function, you will always yield the same exact output when you're dealing with coterminals. So now knowing this, why don't we tackle our example 5 together? Part A asks us to find angles that are coterminal with 30 degrees. So if our theta is 30 degrees, then we're simply just looking at 30 degrees plus 360 n, where n is any element of the integers, and n is not equal to 0. So we can have negative values too. If we plug in -1, this would still be coterminal. It just essentially means we add 360 or subtract multiples of 360. Now let me give you actually numerical examples. We have 390 degrees is an example. 720 plus 30 gives you 750. And then we also have -330. And then -690. Right? Part B is just looking at it from a radian standpoint, but we're also dealing with a different angle. We have pi/3, which is actually just 60 degrees. And so how do we figure out coterminal angles? Now we're going to add multiples of 2 pi or subtract multiples of 2 pi. So pi/3 plus 2 pi n, where n is an element of the integers, so all positive or negative whole numbers, but we also want to exclude 0. So n doesn't equal 0. So some examples of this, all right, well, 2 pi plus pi/3, 2 pi, let's add these, make sure the denominator is 3. So 6 pi plus pi gives you 7 pi/3. That's one example. And then we can do our 6 pi/3 minus pi/3. Sorry, other way around. Pi/3 minus 6 pi/3 makes a difference. Gives you -5 pi/3. And then if you keep subtracting 2 pi, you'll continue to get coterminal angles. So that's where the ... dots keep. And that's it. Example 6, we have find an angle with measure between 0 and 360 that is coterminal with 1,290. So how do we do this? We just want to continue to subtract multiples of 360 until we get it between 0 and 360. So we have 1,290. Instead of doing it one by one, 360 times 2 gives you 720. And then I'm going to actually add another 360 to that to get 1,080. That's the number I'm just going to subtract. And so when we do that, we get 210. Ah, would you look at that? It's between 0 and 360. That's our answer. Yeah, can you just subtract them separately each time? You can, but that takes too long. We want to do it quick and efficiently. And then finally, we're on our third objective for today, determining, I said third, I meant fourth, determining the length of an arc. And so we're really going to utilize this S is equal to R times theta. And our R stands for our radius. Our S stands for our sector length. And then our theta stands for our angle measure in radians. That's really important. A lot of students make this mistake. So angle measure, this is just short script for angle. You may have learned this in geometry. So angle measure in radians. Now, they represent the formula as S is equal to R theta. I always like to represent it as theta is equal to S over R. And that's just because I have a short little way to remember this. I don't know if it would help you out, but my first name is Rachel. My last name is Soik. And my last name will always take dominance over my first. There's a lot more meaning to it when it comes to family. We all share that same last name, so that's why it's in the numerator. It's on top. And so Soik over Rachel gives you your angle theta in radians. Now, if that's helpful, great. Even if it's helpful for one of you guys, awesome. If it's not, maybe you can come up with something else that would help you out. And so now we have this example 7, where we're asked to find the length of the arc. We're given a radius of 10 and an angle of 30. Remember, 30 degrees is in degrees. We need to convert this into radians. Because this is a famous angle, we know that this is pi over 6. And then we're given that our radius is equal to our 10 meters. And so we utilize our formula theta is equal to S over R, Soik over Rachel. And we're asked to find our length, so we want to find our S. We know our R is 10, and we know our theta is pi over 6. So just plug and chug. Pi over 6 is equal to S over 10, and then solve for S. I'm going to multiply both sides by 10. And so we get S is equal to 10 pi over 6, which reduces to 5 pi over 3. And we're done. We can write our units. Radians. Let's answer part B. An angle theta in a circle has a radius of 4 meters. Is subtended by an arc length of 6 meters. Find the measure of theta in radians. And you'll notice that I actually did make a mistake with our units here. I don't know why I wrote radians. It is, our unit measure is in meters. I think I saw the pi and I was just immediately thinking radians. Now, arc lengths are always in terms of the units that they give you. So let's go back to this part B. We want to find our theta. Again, we're going to utilize our theta is equal to S over R. Our S here, they give us as 6 meters. And then our radius, they give us as 4. So when we plug it in, we get theta is equal to 6 over 4, which is reduced to 3 over 2. And with our angle theta, this is now in radians. So 3 over 2 radians. And we're done. So this concludes our section 7.1 on angles. Next time, we are going to be covering our section 7.2, which is right triangle trigonometry. Thank you, and I'll see you guys next time.